We have finished lesson 8 with the introduction of the three elementary transformations on the rows of a matrix. Since they will play a fundamental role in this lesson, let's recap them. The elementary transformations E1 consist in replacing a row with that row plus a coefficient times another row. The elementary transformations E2 consist simply in the swapping of the position between two rows. And finally, the elementary transformations E3 consist simply in replacing a row by that row multiplied by a non-null scalar. We had also introduced the concept of matrix reduced by rows, which is a matrix such that in every non-null row there exists a special element, which is an entry below which in the same column there are only zeros. The first novelty of this lesson is how we can use E1 transformations in order to create special elements in a matrix. Suppose that we fix our attention on the row Ri and we want to create a special element in the position ij. As you can see depicted here, all the matrix elements below aij in the same column can be written as akj with k that goes from I plus 1 until m. To nullify all these entries below aij, we must apply this E1 transformation. That is, we must replace the kth row with itself minus the ith row multiplied by akj divided by aij. This can be verified by writing explicitly the elements of the row k and the row I. How can we do that? Well, we fix the row index to be k, and we let the column index run from 1 to m. Similarly, here we fix the row index to be I, and we allow the column index to run from 1 to m. If we perform the multiplication of all the row entries by this factor, we obtain what is written here, and as you can see, at the jth position, we find that this entry and this entry cancel out, and we remain with akj. Hence, when we subtract the two vectors at the jth position, we obtain akj minus itself, and so this entry is nullified. Let's see this method in action with a very simple example. Imagine that you want to transform this entry in the special element for the first row. Since there are just two rows in the matrix, what you do is to apply this E1 transformation here. That is, you replace the row 2 with itself minus row 1 times A21 divided by A11. Introducing the numerical values of A21 and A11, we obtain 1/2. Look what we have here. We have 1, that is this entry here, minus 1/2 times 2, which is A11. So 2 and 2 are erased, and we remain with 1 minus 1, which is 0. Don't forget to apply the same transformation to all the elements of the row. So we also have to transform this entry here, and we obtain 5 divided by 2. The matrix A' that we obtain is reduced by rows. It has two non-null rows, which are linearly independent, and so its rank is 2. Since an elementary transformation doesn't change the rank of a matrix, we have that 2 is also the rank of the initial matrix A. We can now introduce the practical method to reduce a matrix by rows and compute its rank. First of all, if the matrix A has null rows, Then apply E2 transformations to set all of them as the final rows of a new matrix that you call A1. Then select a non-null element of the first row of A1 and nullify all the entries below it in the same column by applying the E1 transformations that we have seen before. What you obtain is a novel matrix that you call A2. Now consider a non-null element of the second row of A2. Pay attention, the second row and A2, not the original matrix, okay? And then nullify all the entries below it in the same column with the E1 transformation described before, obtaining a novel matrix A3. And then iterate this process until it's possible. The non-null rows of the final matrix that you obtain are linearly independent, and their number is the rank of the matrix A. Let's see this method in action with the following matrix. I chose this entry here to become the special element of the first row. This is an arbitrary choice. I could have chosen also this entry here. If we follow the prescription of the E1 transformation that we have discussed before, in order to obtain 2 as special element of the first row, we have to apply this E1 transformation on the second row and this E1 transformation on the third row. Why do we have a difference between this coefficient and this coefficient? Well, because this is A21 divided by A11, and this is A31 divided A11. If you perform explicitly the computations, you find this novel matrix A1 written like this. As I told you before, the transformations E2 and E3 can be used in order to simplify the computations. In this case, we see the appearance of fractions in A1, and so we can apply 2 times the transformation E3 to multiply both the row R2 and the row R3 of A1 by 4 and 2 respectively. What we obtain is this novel matrix here. Why did I choose those coefficients? Well, because as you can see, the matrix that we obtain has 4 and 4 here. So we can create a special element in the second row of A2 simply through the E1 transformation. R3 goes into R3 minus R2. Notice that we perform a transformation only on the third row of the matrix A2. What we obtain is a novel matrix A3, whose third row is given by 0 minus 0, which is 0, minus 1 minus 6, which is minus 7, 4 minus 4, which is 0. We have finished the iterations because we have for the first row of A3 a special element, for the second row of A3 a special element, and we don't care about the third row. To resume, the matrix A has been reduced by rows to the matrix A3, which has 3 non-null rows which are linearly independent, and so the rank of A3 is 3, which is equal to the rank of A because we have just applied E transformations. I want to stress the fact that the slight modification of the practical procedure that I have outlined above comes from the fact that I have a certain experience with this technique. Of course, we could have avoided the use of the transformation A3 that I applied here, but in doing so, we had obtained a different matrix A3 with the appearance of fractions. This is of course not a problem, but you'll see that when you acquire experience in the process of reduction of matrices, these kind of tricks will come quite naturally to your mind. Let's see another example. Here I'm going to show you how to combine the elementary transformations to achieve a more rapid reduction by rows. First of all, by looking at the matrix, we see that it's convenient to turn this entry here into the special element of the first row, because we have already a 0 in the column in which it lies. In order to do that, if we multiply the second row by 2 and then we subtract the first row, we of course obtain 0 in this position here. So we can perform this combined elementary transformation obtained by this E3 transformation and this E1 transformation in order to get this matrix here. You see that by performing the computations, we arrive to a matrix in which the second column has 2, 0, 0, and so 2 in the first row is a special element. We also see that the second and the third row of the matrix A1 are the same, and so we simply perform the operation R3 that goes into R3 minus R2. What we obtain is a novel matrix A2, which is reduced by rows, because this is the special element of the first row, and all these are special elements of the second row. Notice that this time we have obtained a matrix reduced by rows with only 2 non-null rows. This means that the rank of A2, which is equal to the rank of A, is 2. Until now, we have just talked about reduction of matrices by rows. You can wonder if we can talk about reduction by columns. The answer is yes. Not surprisingly, we say that a matrix is reduced by columns if its transpose is reduced by rows. However, mathematicians prefer to apply row reduction, and for this reason, if the number of columns of A is considerably smaller than the number of rows, then instead of dealing with A, we deal with A transpose and reduce it by rows. The last step towards Gauss' method for solving linear systems is an improvement of the procedure of row reduction that we're going to discuss in the next section. The name echelon comes from the same French word, and for listeners who don't speak French, it means step of a staircase. The reason is that, as we're going to see, the non-null entries of a row echelon matrix form a staircase. If the matrix is a square, then the row echelon form coincides with an upper triangular matrix, otherwise is the most similar version of it. The reduction to row echelon form of a matrix is performed by first setting all the null rows at the end of the matrix, and then by creating a special element normalized to 1 called the pivot in every non-zero row, which is on the right, not necessarily the immediate right, of the pivot of the previous row. As always, the abstract definition seems a little bit involved at the beginning, but if we consider an example, things will become very clear. Let's consider this matrix and let's reduce it to row echelon form. In row echelon form, the special elements, the pivot, are normalized, and we see that there is 1 in the third row. So if we exchange the row R3 and the row R1, we obtain a matrix A1 which has 1 in the first position, thus facilitating our job. I strongly invite you to check that if we want to nullify this entry and this entry, then we have to apply these E1 transformations here, respectively. What we obtain is this matrix A2 with a normalized pivot in the position 1, 1. Now we fix our attention to the second row of A2 and we normalize the first non-null entry, this one. This means that we have to operate this E3 transformation dividing R2 by 6 and obtaining this matrix A3 with a normalized element here in the second row. Now you can check that this normalized entry becomes the pivot of the second row if we perform this transformation here. What we obtain is this final row echelon reduced matrix. As you can see, I underlined the staircase and the two pivots. As a final comment, let me tell you that I'll explain in a few minutes why it is convenient to normalize the value of the pivot to 1. Let's now use the computation of the previous example to show how easy it is to establish if a linear system is solvable or not when its augmented matrix is reduced to row echelon form. Consider the following linear system that can be translated in matrix form with these matrices here. You can see that the augmented matrix of the linear system is this one, which coincides with the matrix that we have examined in the previous example. So we can take advantage of the previous calculations and write its row echelon form like this. Since we have 3 non-null rows, the rank of the augmented matrix is 3. However, if we take a look at the so-called A part of the matrix, this is the A part of the matrix, we see that its rank is 2. In fact, there are only 2 non-null rows in the A part. So we have 3 equal rank of the augmented matrix, different than 2, which is the rank of A, and so by the Roche-Capelli theorem, the system is not solvable. Another way to see that the system is not solvable is to translate back the last row of the augmented matrix into a linear equation. We have 0 times x plus 0 times y plus 0 times x equals minus 1. That is, 0 equals minus 1, which of course is impossible, and so the system cannot be solved. What we have just discussed in this specific example can be stated in general terms. If the augmented matrix of a linear system is reduced to row echelon form and its null rows coincide with the null rows of the A part, then the rank of A is equal to the rank of the augmented matrix, and so by the Roche-Capelli theorem, the system is solvable. Otherwise, the system is not solvable. We have now all the information that we need in order to introduce the Gauss reduction or elimination method to solve systems of linear equations. To discuss the Gauss method to solve linear systems, we first need a definition and a theorem. Two linear systems are said to be equivalent if they have the same set of solutions, including the empty set, which means that they are both non-solvable. This theorem says that if A prime is a reduced version of the matrix A, then the linear system A prime x equals B and the system AX equals B are equivalent. This means that instead of studying an original system, we can study its reduced form, which is much easier, as we are going to see. Let's consider this linear system with matrices A, X, and B written like this, and the augmented matrix written like this. As we have seen before, we can establish if the system is solvable or not by reducing the augmented matrix to row echelon form. We start by exchanging row 1 and row 3 so that we have 1 in the first position of the matrix. Then we operate the following E1 transformations, this one here and this one here, and we obtain this matrix. In this way, we have turned 1 into the pivot of the first row. Then we notice that the second and the fourth row of this matrix coincide. Thanks to this remark, you can verify that if we perform the E1 transformations written here and here, we obtain this matrix. As you see, we have almost done. In fact, in the second row, we have 2, under which we have just zeros. And in the third row, we have a -6, under which we have 0. So if we divide R2 by 2 and R3 by -6, we obtain the row-reduced echelon form for the augmented matrix of the linear system. We now notice that the final row is 0, and so, for what we have said before, the rank of A is equal to the rank of the augmented matrix, which is 3, because we have 3 non-null rows. Furthermore, recall that we have 3 unknowns, x, y, and z. So, thanks to this equality and the Roche-Capelli theorem, we can say that the linear system is solvable and it has a unique solution. To find this solution, we transform back the echelon reduced augmented matrix into a linear system. Notice that it's useless to write the last row. In fact, this gives the identity 0 equals 0. Hence, if we consider just the first 3 rows, we obtain this system here. We solve this system using a bottom-up strategy, meaning that we start from the last equation and then we go up. Introducing the value of z equals -1 into the second equation, we obtain y as 7.5. Introducing then y and z in the first equation, we obtain x equals 10. To conclude, this triple of values is the unique solution of the linear system. This example gives us the opportunity to explain why it is useful to normalize the pivot of a echelon-reduced matrix to 1. As you can see, the unit value of the pivot allows us to avoid having coefficients in front of the variables. Thus, we can simply solve the system by substitution as we have done before and save time. Let's consider another example. The matrices associated to this linear system are these ones, and the augmented matrix is written here. To reduce this matrix in row echelon form, we need to nullify these entries here. For that, we perform these two E1 transformations. We obtain this matrix, and if we divide the first row by 2 and the second row by -3, we obtain this other matrix. As you see, we have 1 and -1 in these positions, so if we perform the E1 transformation R3 that goes to R3 plus R2, we obtain the echelon reduced matrix. The last row of this matrix is null, which means that the rank of A and the rank of the augmented matrix agree, and so the system is solvable. We have 2 non-null rows in the final reduced matrix, and so the rank of A is 2. However, the number of unknowns is 3, and so the system will have infinite solutions. Moreover, thanks to the nullity plus rank theorem for matrices, we have that the nullity of A is 1. In fact, A is a square matrix, and so its rank plus its nullity must give back the dimension of the matrix, which is 3. We will use this information later, but for the moment let's continue with the solution of the linear system. We already know that we can discard the last row of the reduced augmented linear matrix, and if we use the first 2 rows, then we can transform them back into this linear system here. This system can be immediately solved, and the solution shows that x and y are expressed with respect to the free parameter z. This example offers us a nice opportunity to compute the kernel of the matrix A explicitly. We know that by definition the kernel of A is given by the column vectors x that satisfy the homogeneous system Ax equals 0 associated with the linear system Ax equals b. Now, in matrix form, the homogeneous linear system can be written like this, and its augmented linear matrix is this one here. If we repeat on this matrix here the sequence of operations that we have used before in order to reduce to echelon form the augmented matrix of the original system, we obtain this matrix here. The corresponding homogeneous system is this one, whose solution is written here. So we have that x and y depend on the free parameter z. This means that all the vectors belonging to the kernel of A have this representation that can be also written as z times this vector here. Such a result was expected, right? In fact, we have seen that the nullity of A, that is the dimension of its kernel, is 1, which means that the kernel of A is generated by just one vector. Thanks to the extensive analysis of the examples that we have made, we can give the general practical method to solve a linear system with the Gauss reduction method. Given the linear system Ax equals b, the first thing to do is to reduce the augmented matrix to row echelon form. The second thing to do is to establish if the system is solvable or not by checking if the null rows of this matrix are the same as those of its A part, in the sense specified in this theorem here. If the system is solvable, then it can be solved by substitution with the bottom-up procedure that we have seen in the last examples. Regarding the uniqueness of the solution, by the Roche-Capelli theorem, we have that if the rank of A is equal to the number of the unknowns, then the solution is unique. But if the rank of A is strictly inferior than the number of unknowns, then there are infinite solutions, and there are as many free parameters as the nullity of A. Let's finish this lesson by applying this procedure to one of the exercises that I proposed at the end of this chapter. We are at page 108, and the exercise asks us to solve the following linear system by first guessing how many solutions the system can have. We are at page 109, and the first thing that we notice is that the coefficient matrix of the system has 5 columns and 4 rows, hence its maximal rank is 4. However, the number of unknowns is 5, hence if the system is solvable, there will be an infinite amount of solutions with at least one free parameter. Keeping this information in the back of our mind, we build the augmented matrix and then we reduce it in echelon form. I strongly invite you to pause the video and try and do it by yourself. Now let's check if your solution coincides with mine. The transformations that I applied are written here, and the matrix that I found was this one. In this way, I created the pivot of the first row. Then I performed these transformations, arriving to this matrix here. And finally, I created the pivot of the second and the third row with these transformations. So this is the reduced echelon form of the augmented matrix. Notice that there are no null rows, so the system is solvable and the nullity of A is 1. So our initial guess was right, and we have an infinite amount of solutions with just one free parameter. By transforming back this matrix into a linear system, and by solving it with the bottom-up procedure that we have used, we find that the solution is indeed this one in which we see a free parameter.